Welcome to the second part of the YouTube manual of the virtual lab experiment. This part is going to be about the feedback control. And this part is going to be much more difficult, at least for me to handle. Well, it's both a little bit more difficult to explain the whole thing, but more than that, it's going to be a little bit difficult to handle all this stuff with two monitors. So I hope I can do it well enough. So I would like to first talk about a couple of concepts. I would like to make it much more clear. So these are my notes, as I said previously. Hopefully I'm going to be talking about them. This is the part where we were left. So we were through with step changes on the manipulated variable to understand the dynamics of the process. And when I say dynamics, I'm talking about the dynamic relation between manipulated variable and the controlled variable. Actually, the whole dynamics also should include the dynamics between, or the relation between, the disturbances and the controlled variable. But in this virtual experiment, we are not going to consider that relation. For the whole experiment, we are going to take the disturbance to be constant, just making small fluctuations around the constant value. So this part will be only about servo control. But actually, in real life, most of the time, actually, the more frequent control action is the regulatory control action. Because servo control is when the people who are in charge of the process would like to make a change in the manipulated variable, or would like to make a change in the controlled variable. So therefore, they just give the set point, and the controller brings the system to the new set point, changing the manipulated variable. This is less often, because the requirement to change the set point depends on a couple of things, maybe some changes in the economic conditions, or maybe and demand in the increase or decrease in the production, or things like that. On the other hand, almost every second or maybe every minute, or at least in a much more frequent manner, the disturbances will usually are going to be perturbations in the disturbances. So therefore, controller should, the primary aim of the controller should hold the system at the set point, preset set point, in spite of those disturbances. And therefore, regulatory control is the more common control, whereas servo control is the less frequently applied control, let's say. So in order to deal with those disturbances, we should also understand the dynamics of these disturbances. But within the content of this virtual experiment, as I said, we are not going to go into that. So it's going to be all about servo control. Okay, so in servo control, the idea is pretty much simple. We would like to bring the system to a new set point. So with respect to our virtual experiment, remember our virtual experiment, we had two tanks, and we are interested in the tank in the tank at the bottom. We would like to change the operating point of the water height. For some reason, we are not content with the current operating point. Let's say it is 21.7 centimeters. I think the regular operating conditions or the design conditions, we would like to change that to, for instance, to 25 centimeters. Why that? There may be many reasons. As I said, there may be a change in demand, or some economical reasons, some things related with safety, or other issues. But it's not only a single operating point that you are going to run your system, that you need to have that flexibility. First, let's understand that. So the problem is, for instance, we would like to change the set point from 21 centimeters to 27 centimeters, or 21.7 centimeters to 23.7 centimeters, because that was the operating point. That's why this is a floating number. So how are we going to do that? Now, hopefully we have already done a couple of step changes. And if you go back to those step changes, we know that when we changed the flow rate from 1 liter per second to 0.90 liters per second, this change will happen. I'm not going to go through that, of course, you can watch the video, but basically there was a response such as this one, and that was actually when you change the flow rate from 1 liters to 0.9 liters, this is the flow rate, the outlet flow rate from 1 to 0.9 liters per second. Time after you make this change, this height will change from 21.7 to 23.7. How do we know that? Actually, we have tested and obtained this result. So when during an operation, when we are operating the system again at 21.7 centimeters, we would like to bring the system to 23.7 centimeters, we can just use our memory, or we can just take our look in our notes, or we have already applied this change during our tests. So if we do the same thing again, we are going to obtain the same result. So this is a very human behavior. I mean, a typical human behavior. We have done something previously, so do it again so that you obtain the same response. Well, we have two problems with that strategy. First of all, if you recall, this response was due to the open loop time constant of the process, which was about something like maybe 100 to, well, we have found that it changed from operating point to operating point, but it was in the order about 100 or 150. So reaching the steady state will somewhat like be equal to at 5 tau values, maybe. So this value seem to be a pretty much large value. First of all, maybe up to 500 seconds or maybe 400 seconds. So we have to wait for a couple of minutes to reach that value. So one thing, can we do it faster? Just a very simple strategy that usually if you would like to heat, for instance, a room or your car, you do not just bring the system from, let's say, by experience, you know that from 1 to 0.9, when you decrease it, it's going to happen. What you intuitively would do is you first would decrease it to a much lower value, maybe to 0. Then after a while, you bring it to 0.9 so that there's going to be steep increase, then slightly conversion. So our mind, without realizing, maybe uses a pretty much intelligent control strategy. First, open the valve as much as you can, then close it. But maybe we can do it better, or even how can we, how are we going to explain this to a computer so that an automatic control is going to be achieved? Okay, so even that strategy is just using memory or previous experience is not a very good strategy, because bringing the system to a constant flow rate, outlet flow rate, and maintaining at that value is going to be a too slow response, because we are just going to be content only on the open loop time constant. But probably you know from your process control lectures, when you bring the system to when you run the system in a closed loop manner, the closed loop time constant is much smaller than the open loop time constant. And one of the reasons why we use closed loop processes is to fasten, to speed up the response of the process. And this is achieved by changing the velocity, the inlet flow rate. We do not just make a step change and let it go that manner. The manipulated variable changes automatically. And there's another problem with that approach. Even this response weren't slow, we would need a very large lookup table for all the possibilities. Let's say that from 27 to 23.7 to, then we would like to make a change to 29.5. Then we would again need to look up in our infinite wisdom, that notebook which contains infinite wisdom of information, I may say. So it is impossible to obtain all these different couples of combinations, set point changes, right? It's maybe we could have done a couple of tests, but that's it. So that much of a large lookup table is impossible. So therefore, this is not a practical, neither practical nor a feasible solution. One solution here is to use the inverse of a process model. What do I mean by that? And this is actually forms the basics of model-based control, which is not about this experiment. And this is sometimes in some control undergraduate courses only mentioned, or it's not mentioned. It may be a little bit of above the introductory level. But I'm going to just talk about it very briefly, not the actual model-based control, but it's going to be just trying to explain the spirit of that, because I would like to use some idea there that is buried inside in Cohen settings. So here is the idea. Let's say that previously, well, actually, this I think some results something like this was obtained. When u was equal to 1 liters per second, that was the steady state operation. And when u is equal to 0.9 liters per second, the steady state operation was equal to 23.7 centimeters. I hope that that is the case in the first video, because I have changed the many numbers during those preparation of these videos. Even if that's not the case in the first video, that's no big deal. So please take that as it is. So actually we change and we obtain a curve, and now I'm only interested in the final and the first values here, because this was the old operating point. Now this is a new operating point, old one, new one. So basically what we do is we give a change of minus 0.1 liters per second, final condition minus initial condition. So it's going to be minus 1 liters per second in the outlet flow rate of the first tank. And the second tank increases its height by 2 centimeters. Now, what we call steady state gain is the ratio of the difference between the perturb Y output values and also perturb input values. So for this case, it's going to be the delta H steady state values, which is going to be 23.7 minus 21.7, which is 2 centimeters, over 0.1 minus 0.1 liters per second. This is going to be the steady state gain of our process. And we find that when we divide it, the result is going to be 20 centimeters over liter per second, minus with the minus sign. That's an important thing, of course. So this means that, okay, I have 20 here. This means that this is the steady state relation between the change in the manipulated variable and the change in the output variable or the controlled variable. So it means, in other terms, if you give a change of 1 liters per second, so if you increase the input by, which is when I say input, I'm talking about the process input, not the physical input. Physically, this is the outlet from this first tank. So it means if you increase the flow rate, the outlet from the first tank, by 1 liters per second unit, then the change in the height of the second tank will be minus 20 centimeters. If everything is linear as it is supposed here. So I think for many of you, this is pretty much clear, because this is something that you've probably done in process control, or even just using your logic, you can come up with this result. But note that the steady state gain is exactly the very same gain in Kp tau s plus 1 thing. So it is the very same thing. Actually, this Kp, the meaning is exactly this one, the relation between the steady state values without the dynamic part. Now, what do I mean by the inverse of the process? Now, this is, now I do not include the dynamics of the process. I'm only interested in this steady state values. In reality, I should be also interested in the dynamics of the process. Therefore, I do not care about the first problem here, right? I just leave it. I just concentrate on the second problem. In a more rigorous model-based control, the first problem should also be handled. That's why I only concentrate on the steady state relation. So here is the question. If my aim is, for instance, to change the set point or the running conditions from 20.5 centimeters to 25 I'm sorry, this should be centimeters to centimeters. Let's say that our process, the liquid height is at 25.5 centimeters, and I would like to increase this height to 25 centimeters. So a change in set point. So actually a change of 4.5, not liters per second, centimeters. I would like to have this change. So now I can invert the model. What do I mean by that? Here, I know this part. 4.5 is going to be equal to minus 20 times delta U steady state. I do not know this value. What I know is this one, the desired change, and I know this minus 22, which is my steady state model. So what I do is I invert it. So therefore I put it here. So it's going to be minus 4.5 over minus 20, which gives me this value. So therefore U should be changed, or the change in U, steady state value of U, should be equal to minus 0.25 liters per second. So what I do is, since the initial value is 1.0 liters per second, let's say if this is the case, of course, this doesn't give me 20.5 value. I messed up here, but that's not the big deal. So what I do is the new U steady state value should be equal to 1 plus or minus here 25.75. So if this model is applicable for all operating points, right, and it's 100% accurate with no measurement error, no error, then if the initial condition with a steady state value of 1 liters per second outlet, if the height is 20.5 centimeters, and if I would like to reach 25 centimeters, if you just blindly, without doing anything else, if you just decrease this flow rate from 1 liters per second to 0.75 liters per second and let the system go, it's going to reach really 25 centimeters. So the second condition would be satisfied. Therefore, instead of a lookup table, a model, a steady state model, actually works just as fine. And the model in model-based control, actually, you can also include the dynamics part, which of course I'm not going to do it. But because the reason here is not to emphasize what model-based control is, I'm going to try to connect it to feedback control. But still, we have problems. Now, the most important problem here is this works only if the process is linear. Because if the process is nonlinear, such as the one that we have, the process parameters are likely to change from operating point to operating point. And I have already shown you that tau pretty much changes, it significantly changes from operating point to operating point. And maybe if you go through a sufficient number of different operating points, KP is also going to change. I haven't checked that out. So if we have a nonlinear model, this change, note that this is a model of change. If we apply this change on steady state values, wherever the steady state value, it doesn't matter, this model says that this is going to be applicable. So again, note that all the models related with Laplace transforms are also relate the changes. Change in U to change in Y. For any steady state value, we expect it to be applicable. But this is going to be only the case if the process is linear. If the process is nonlinear, then this is not going to work. Okay, and we have another problem. Over all this operation, the perturbation in disturbance or the disturbances should maintain their values. If they change their values, again, even if the process is linear, this model is not going to be also applicable. Think about something like this. During this operation, let's say, while we are trying to bring the system to 25 centimeters, then there's going to be a disturbance in the system, or the disturbance of the inlet flow rate suddenly changes by 0.5, or maybe slowly changes by 0.5 units per minute per hour, whatever. So there are going to be changes in the disturbance. And when this is the case, then this calculated value will be obsolete. It's not going to be applicable. So therefore, when you reach this value and apply this value, you are not going to be obtaining the very same, this desired water height, because there's going to be more water coming from the top or less water coming from the top. And these calculations are based on the previous state. And since this is usually the case in process industries, such a very simple scheme would not work. Or you need to control many things so that it's going to, or you need to be careful about how to make it work, because model-based control is a very proficient area, I may say. So a better solution, a more practical solution is, so this, instead of this whole strategy is, why use a model or try to calculate the exact value that is required to bring the system to the set point? Instead of that, forget about the process model, behave as if we know nothing about the process model. So how are we going to bring the system to the desired set point? Use a feedback control strategy. What does feedback means? I'm just talking about just two guys talking with each other. The guy who comes with the concept, think about that previously people think that model is required. In feedback, you don't need the model. What you only need is the set point. What is the value that you would like to reach? Okay, and the current value. As long as there is error, apply the input. Let this be your strategy. If this is your strategy, you don't need to know anything about the process, then you are going to be able to control it. If you are going to heat a room, you do not take a pen and come up with the mathematical model of the room. You just open turn on the radiator and increase heating as much as you like. When you feel that, and during that heating, you check the temperature of the room just by feeling it. You have a set point in your mind probably when you feel warm enough. Do I feel warm enough? No. So let me continue increasing the heat. Do I feel warm enough? Yes. So let me close heating, or this much of heating is going to be maintained. So this strategy is the feedback control, and you don't need a mathematical model for that. Be careful with that issue, because when I took the process control course, actually on the fourth year when I was a student, actually I couldn't understand that concept, because there were everywhere the mathematical models, all those models of the process. Actually, they are not used for control purposes. They are just used to demonstrate what's going on. So basically, process model is not required. So find something called, which is called error, y set point minus y, and you don't need even each of these values. What you only need is the error, the distance or the deviation from this request set point or the actual value from the set point. Then the change in input variable will be a function of this error, and change this as long as the absolute value or the error itself is not equal to 0. That's a great strategy. And you seem to have no need of a model. But we have a problem here. What is going to be this function exactly? And this function, I'm not going to go into those, but we have P control, PI control, PID control. And in this virtual lab experiment, we're going to be only dealing with PI control, where actually most of the industry is based on PI control. Derivative control is because susceptible to noise. There may be problems with that. So I'm going to just concentrate on PI control. So basic, the functional form of PI control is this one. So we calculate the error, and then what we do here is, we take this error term, and plus we take the integral of this error term from the beginning of the time, multiplied by a constant, multiplied by another constant. And this function gives us how much change in the commanipulated variable is going to be employed from a steady state value. Again, note that this does not give us the absolute u value. Still, there is a linear assumption. The absolute u value is going to be the steady state u value, which is the starting point u value, plus delta u. So the change in delta u is calculated by this manner. And also think about the feedback, all those block diagram things. That block diagram is only computes delta u. the real U is going to be always equal to this value. It's called bias in process control, not to be confused with the bias in statistics. Okay, so basically one can say that this function is equal to some current error multiplied by Kc and sum of all previous and current error terms multiplied by Kc tau I, and you add them together. So one way to interpret this is the change in the outlet flow rate for our case, or the manipulated variable, is going to be a weighted sum of the current error, which means currently the desired set point is, let's say, 25 centimeters, whereas we are at 20 centimeters. Find the deviation between them. It is 5 centimeters. Let's say it's a large value. So apply, multiply it by some constant and apply that much of control. But that's not only that. Also consider the previous error terms. If we have started with that, the previous error terms is just 0, so no error has accumulated yet. But as time continues, error will accumulate. So if there is a large amount of error accumulated in the history, its effect will be larger and larger. And these are the weights of those two terms, the current error and the old accumulated error term. This is basically what it means. So, for instance, one very important thing, let's say that you are at 24.9 centimeters. A very little error is remained. Now, so for this case, so what if, let's say, Kc is not a very high value, current error is very small, so the contribution of this part is going to be very small. So delta U from the first part is going to be a very small contribution. Delta U1 is going to be almost equal to 0. However, if we have a long history or a large number of error terms in our history, and from 20 to 25, we had many error terms, still we are going to have a large value of U2, which is the second part, call it delta U2. So delta U is going to be equal to, maybe this part is going to be 0, but there's going to be a part which is going to be substantial in determining the delta U value. So there's going to be still that delta U value, and this is the reason why integral action, on the integral action, you can reach the set point. If you only use this value, note that as you get closer to the set point, then your additional delta, that additional input, this term tends to go to 0. And if this is the case, your input turns to be closer to the initial value, manipulated variable value, but initial variable manipulated value actually has given the first initial steady state value. So what you would like to reach that value here. So when you use a P-only controller, you are always stuck somewhere in between those two values with some offset. So this offset can be only closed by using the PI control or the integral term. Anyway, so here is the problem. Now we have Kc and tau I. They are just parameters. Call it A1 and A2. You can actually write two independent terms for them. These are the weights of these. How are we going to determine these weights? So in other words, when the controller finds that we have an error of 5 centimeters, it's going to multiply it by some Kc, and delta U is going to be equal to that one initially. So initially this part is going to be almost equal to 0 because the integral is going to be equal to 0. The problem is, so there's an error of 5 centimeters, change the valve. That's great. The question that, let's say that there are two guys in the computer world. The first one says that, okay, 5 centimeters of error, change the valve. But the other guy says that in that computer world, how much shall I change it? Because this case, if this is equal to 1,000 or whatever, then it's going to be 1,000 units of change of the manipulated variable valve. Or if it's equal to 0.00001, if Kc is equal to that, then it's going to be a very small value. This equation by itself only says that change delta U proportional to the error term. That's it. However, still we need the value of Kc, and very similarly, we need the value of tau I. And these unfortunately depend on the process model. So even Although in feedback control, it is not model-based control, so you do not necessarily need a model to calculate the control action. That is the fine distinction. You do not use the model to control to compute the control action, but you determine the control action using this formulation. The parameters in those model are usually determined using the process or the model of the process. That's the interesting or the interesting communication between model, process model, model-based control, and feedback control. But there is one very important difference compared to model-based control. In model-based control, this model should be perfect if you would like to obtain no offset, right? This 20 should be really exactly 20 because what we do compute, everything depends on that value. On the other hand, these values, let's say that the optimal value, I'll try to explain what optimal is. Let's say 12.5 or whatever the unit is KC. Instead of that, if you write 10 or if you write 15, most likely the process will still converge to the set point. So maybe it's not going to, it's going to be a suboptimal trajectory, yet still the control action will work fine. So there is that important distinction between model-based control and feedback control. The role of the model in feedback control in determining these Kc and tau I values are, are not very, how can I say it? You don't need to be that much rigorous. You do not need a very accurate model. An approximate model for determining these values will be sufficient. And in most cases, we are going to be using that approximate model as an initial guess, which we are going to do. Then we are going to, by a trial and error, we are going to tune the parameters. So finding the correct Kc and tau I values, even if correct Kc tau I values is something like the concept, something like that exists, because as you are going to see, it's a bit of meaningless talk about the correct or the optimal Kc and tau I values. It depends from which perspective we are talking about. You don't need a very, very good model. An approximate, a general idea about what's going on, some idea about the general terms of the model is sufficient. So I think how this works is not very much important, but this part is important. So think about the case. Let's say that we have a process with small Kp, and let it be positive. I'm not talking about this process. And we have a steady state relation such as this one. So it looks like model-based control thing. We found a steady state relation and we have a Kp value pretty much small. So, and we find an error. And that error is a little bit of a large error. So we would like to bring the system, right? So the delta Y value, steady state value, the value that we would like to reach is pretty much high. And how is that possible? It's going to be actually equal, by the way, these are going to be delta. So delta Y is a very large value. Kp is not a very large value. And we would like to estimate this U value. Or let me get rid of the steady state. How much U should change here? This is the idea. So in this case, what we do is we put here this term Kp and we have calculated delta U. Actually, I have just done the very same thing I have done here. Nothing else here. So what I mean is here in P only control, and note that this delta Y here will correspond to exactly the error because it's going to be the set point minus Y. This is the last point I would like to reach. This is the initial point. Therefore, this is going to be error over Kp. This is going to be delta U. Of course, this is going to change at every step for P only controller or under feedback controller. What I would like to say here is that now compare it with this equation. This is delta U is equal to Kc times error T. So initially delta U is going to be Kc times error T. Since this is error T, Kc is actually equal to 1 over Kp. So what this is, of course, it's not that much simple, but what this simply says is the proportional gain of the controller, the KC in this algorithm, in PI control algorithm, should be basically proportional to 1 over KP. If the steady state gain between the manipulated variable and the control variable, if it's a small value, then you need to open the valve too much so that you get the desired response. And I think I said it correctly. If you like, you may rewind this, listen to it again, because it's difficult for me to say it again. Let me say the opposite one. If the KP value is large, between the manipulated variable and the input value, I'm sorry, response variable, which means you change the valve a little bit and the height drastically changes. Then if you would like to change the height at any value, you would not apply the valve at too much action. The valve action is going to be small. Therefore, a large KP results a small KC value. And this relation is 1 over KP KC. Now, if you go back and check Cohen-Coon settings, note that I will not talk about in detail Cohen-Coon settings. I haven't talked about process reaction curve. I expect you have learned this stuff from the process control course. But in Cohen-Coon settings, once you obtain that first order plus that time thing, which is K exponential minus, in terms of this is going to be tau P, and we have KP tau P S plus 1. This is the model, first order plus that time approximate model that we obtain here. Now, these are the PI control settings. And for KC, we use 1 over KP here. This comes from that part. Of course, it's not that much simple because as we can see, there are more of these. But let me also talk about this second term here. Why do we have tau P here? Think about the case something like this. We have a room and we have a much smaller room. Radiator here, radiator here. Now, this room has a larger volume, therefore its tau value is greater than the second room. If you would like to, and let's say the very same radiator is connected here in these two rooms, we have the same radiator. If you would like to heat this room and also this room and call this Q1 and Q2, for which of these rooms you are going to apply a higher heating? Of course, Q1 is going to be greater than Q2 to obtain the same change in or same increase in T. Therefore, actually KC, note that KC is totally related with this input. When is going to be proportional to tau P. And that's what you actually see here. So as the time constant of a process is higher, it means it's going to be slower. We would like to increase the proportional gain of the controller. And if the process gain is larger, then we are going to decrease the proportional gain of the control. There's of course also the dead time issue. When you have dead time, you should be careful. We don't want to blow things because okay, that's too much detail, and I'm not going to go into tau I because then it's going to turn into a process control course, which is not the aim of this experiment.